Greetings. We are electrical engineering students from the University of Puerto Rico at Mayagüez, and we will be presenting our capstone project, the headset controller for an RC car. The team is composed by Enrique Suarez and Adalberto Velez. We will be presenting the general design and development of the system and the results of the project. Hi, my name is Enrique Suarez, and I work on the software development and the transmission station design and implementation. According to the statistics unveiled by the Christopher and Dana Reeve Foundation, about 150 people in the United States live with some form of paralysis. Current technology allows people to develop tools and toys capable of being operated through alternate methods, all in an accessible manner and relative ease of understanding. Our main objective for this project was to develop a system capable of using head movements to move an RC car, be it as a tool to survey areas or as an entertainment device by utilizing components with the lowest expense and simplest design possible. The transmission station uses an Arduino Uno as its computer, capable of providing all functionalities needed to process the data to be used and send it to the RC car. An MPU 6050 accelerometer and gyroscope is connected to a 3.3 voltage source and uses two analog pins for the movement reading. The radio frequency module is also connected to the 3.3 voltage source, and a capacitor is used to reduce the noise in the transmission to the RC car. The transmission station also includes two buttons connected to a 5 voltage source. A button is used for calibrating the user's head movement limits. While calibrating, a buzzer connected to a transistor will make a beeping noise to indicate the head position limit being calibrated at the time. The other button is a stop button, and it's used to send the instruction of stopping the motors of the car. An alternative to the stop button was implemented for users not capable of pressing the stop button as an emergency measure, and it is connected in parallel to the stop button. An external reset button was added whenever the system stops running or presents any error in communication.
Hi, my name is Adalberto Velez. I'm an electrical engineering student. I've been working with the RC car on the hardware side and the 3D printed designs. Right now, what we can see in the schematic of the receiver, we used an Arduino Mega alongside with the PCB that was manufactured to be connected to the NRF servo and speed controller. Also attached to the Arduino Mega is a push button to reset the system, and also a voltage reader connected to a buzzer if voltage goes below a certain level. Specifically for the motor, we used a LiPo battery, and for the Arduino, we used an nickel metal hybrid battery connected to a voltage regulator. Now for the PCB design, we wanted to integrate this system as simple as possible, so it had the capability to use JST connectors to interchange components if it was necessary. As we can see, this is the manufactured PCB with the JST connectors soldered to it, and also it has one capacitor and two resistors for the voltage reader, and the capacitor is for the NRF. By using a small RC car as the one used, we integrated the PCB to the Arduino board, voltage regulator, and batteries. To integrate all these components in such a small car, it was a bit of a challenge. As we can see on the picture above, the WISE camera or Wi-Fi camera with a custom RC rack to accommodate all the electronic components, and also an all-around bumper.
The transmission station code starts by initializing module libraries, parameters, and pins used on the Arduino board. The accelerometer reads the movement gathered. While the stop button is not pressed, the Arduino will keep recording the raw sensor data and process it. The user has the choice to calibrate the system or not. If calibration is activated, it will start by calibrating the back limits, reading the angle of the head, and store it in a variable. The same process is done for the front limit, left and right, until calibration is complete. Each calibrated limit will be accompanied by a buzzer sound, indicating to move the head to the other limit. After the calibration, or if the user decided not to calibrate, the data being received of the head movements will be converted into readable values, once in respect to the y-axis and the other to the z-axis. The y-axis refers to velocity, while the z refers to steering angle. Will keep repeating itself until the user activates the stop function, making the loop come to an end. The RC code starts by initializing the module libraries, parameters, and pins to be used. If data from the headset is not received, the reset button should be pressed. If received, the Arduino Mega will read the value sent by transmission. This decimal integer, converted previously by the TX, will enter a conversion process, where the value will be converted back into an 8-bit binary data, and it will be separated into a pair of 4-bit binary values. These interior are processed through the mapping function, where they will be turned into speed and angle values capable of operating the speed controller and the servo. After this is done, the Arduino will enter the voltage reading function, where it will read the battery level. If the battery is low, a buzzer will start making a noise indicating it has low voltage. If battery levels are good, it will keep going okay, and the loop will keep on receiving values sent by transmission.
The rack that was made for the camera, which was mounted on top of the RC car, and the components are inside of what we see in the first picture. It is two pieces and are tied up with zip ties. For the puff switch design, taking inspiration from Mauricio Lizama's puff switch, which he made with an audio jack, clear tube, sticks, and metal clips. We redesigned this for it to be 3D printed, and taking the same mechanism, we inserted the clear tube from below. As we can see on the right hand picture, the yellow bar is where the metal clip is located, and on top of that, in the picture to your left, there are two clips attached to the 3D printed and two wires. When the air is blown from underneath, the metal clip that's in between makes contact with the other two metal clips, therefore functioning as a push button. In this part, we can see the earpiece cover. Its function is to protect the NPU sensor, which was mounted to an earpiece. And there's also the transmission box that was also 3D printed and designed for it to mount the Arduino board and other components as the push buttons.
We first tested how the movement is interpreted by the servo motor as steering values. After testing the servo individually, we applied the code logic to activating the speed controller and seeing the behavior with the steering motion. After fully developing and finishing the system, testing the transmission station connection, movement reading and processing of the data, and analyzing the car's response, we concluded that the headset system can be used in a comfortable and adjustable manner thanks to the calibration function. The transmission station is also capable of processing head movement and sending it to the RC car as velocity and steering values accordingly. And the RC car has a range of connectivity of around 10 meters indoors and 20 meters outdoors.
Here we can see how we tested the RC car in real life and how it is controlled with head movements. After testing the prototype, there are some recommendations that we suggest for future improvement. One of them is change the gear ratio to add torque, put a sensor in the car to avoid collisions, change the ESC controller for better control, change the RF module for a higher range of signal, put a physical speed modulator, add a point-to-point camera instead of a Wi-Fi camera for better connection, and reduce noise signal. I really hope you enjoyed our presentation. Thanks for your attention.